All right, so you wanted a deep dive
Yeah.
into modern reinforcement learning.
Yeah.
And, well,
We'll give it to you.
we've got it for you.
That's right.
We're talking self-learning robots,
Yep.
AI mastering games, all that kind of stuff.
The whole shebang.
The whole shebang, yeah.
Yeah.
We've got these college lecture excerpts to help guide us, and thankfully we've got an expert on hand to help break it all down.
Absolutely.
So reinforcement learning, or RL,
Yeah.
as the cool kids call it.
That's right.
What
It's
in
all
Annabella?
about it's all about making decisions, teaching an agent, which could be
Okay.
a physical robot or a piece of software, to make really good decisions.
Oh, so like it could be a program.
It can be just a program.
Okay.
Yeah, just a computer program. And imagine it like it's playing a game.
Okay.
The agent tries things out, sees what it gets rewarded for, and learns which actions lead to the best outcomes.
So it's not like someone's programming the answers into it.
It's figuring it out on its own.
That's right.
By trial and error.
Like learning to ride a bike.
Oh, okay.
You don't get a manual, you just try and wobble and fall, and eventually
Yeah.
you figure it out.
Right.
Through trial and error in an RL, those falls
Yeah.
are actions that don't get rewarded,
Okay.
and the agent learns to avoid them over time.
Okay. That's starting to make sense.
Okay.
But this reward idea,
Yes.
does it always know right away if it did a good job?
That's a great question.
Or is it
Well,
not
necessarily
something
delayed thing.
It can be delayed, and that's where it gets really interesting, because sometimes an action might seem good in the short term, but actually it's not good in the long term.
Right.
And RL agents have to grapple with this all the time.
Like a financial
Like a financial planning AI.
thing.
Yeah. Quick buck today might sound great,
Right.
but investing for the long haul is usually better.
Yeah. So how does the agent
Right.
figure that out?
So that's where this idea of a discount factor comes in. It's a way of weighting future rewards mathematically.
Okay.
So a high discount factor means the agent's more patient,
Okay.
willing to wait for a bigger payoff.
Uh-huh.
A lower one means that it wants the reward now.
Instant gratification.
Exactly, instant gratification.
It's kind of like people, too.
It's just like people.
Yeah.
That's right.
So is there anything else about the way that these RL agents learn that's similar to how we learn?
Yeah, absolutely.
Okay.
So one key concept is a Markov decision process, or an MDP.
An MVP.
And it's basically a framework for thinking about how the agent interacts with its environment.
Okay.
So we break things down into states like where is the agent in the game?
Okay.
What are the actions or choices that it can make?
Right.
And what are the rewards or the feedback that it gets for making those choices?
So like a set of rules for how it navigates its little world.
Precisely.
Okay.
And the interesting thing about this is something called the Markov property. And basically it assumes that the future only depends on the present state and action. But it's the whole history.
It matters.
Yeah, it's
You're right.
right.
In real life, our past experiences shape our choices.
Yeah.
You're absolutely right. The Markov property is a simplification,
Mm-hmm.
but it makes things computationally manageable.
So it makes the problem solvable, basically.
Yeah, it makes the problem solvable.
Okay.
And even with this assumption, modeling real-world complexity is incredibly challenging.
I can imagine.
So imagine an autonomous driving AI.
Oh, yeah.
It has to consider road conditions, other
Yeah.
cars, pedestrians, weather,
How do you even
all sorts of things.
program in what good driving is?
That's right. And that's another key challenge, is designing what we call the reward function.
Oh, okay.
You have to translate those complex goals like safe and efficient driving into numbers
Okay.
that the AI can understand. And sometimes these goals can even conflict, like speed versus fuel efficiency.
Right, right.
So how do you balance those things?
Yeah.
That's true.
Yeah.
Yeah, so we've got this agent learning by trial and error in this complex environment, trying to maximize its rewards.
Yes.
But how does it know which states and actions are good?
That's right.
Does it keep a tally in its head or something?
Not quite.
Okay.
So it uses something called value functions.
Value function.
These are functions that estimate how good it is to be in a particular state or to take a specific action.
Okay.
So they're kind of like the AI's internal compass, guiding its decisions towards the most rewarding outcomes.
Okay, so there are different types of these.
There are different
Value
types.
functions.
There's something called a state value function, which tells you the overall value of being in a particular state,
Okay.
taking into account all the future rewards you might get.
Okay.
And then there's an action value
Yeah.
function, which is more specific.
Okay.
It tells you the value of taking a particular action in a particular state.
So like in the real world, what would that look like?
Okay, so imagine an AI that's designed to play a strategy game like Go.
Okay. I've heard of Go.
where it has the opportunity to capture a group of the opponent's stones.
Uh-huh.
The state value function would tell the AI how valuable that position is overall,
Got it.
taking into account all possible outcomes from that point onwards.
Okay.
The action value function would tell the AI how valuable it is to take that action of capturing the stones,
Okay.
taking into account the immediate gain, but also any potential drawbacks that might come later.
So it's weighing the
Yeah.
options. Okay. But how does it actually calculate these values
Okay, so
for all these different states and actions?
that's a great question. And to answer that, we have to distinguish between model-free and model-based RL methods.
Okay, model-free versus
Model-based.
model-based.
That's right.
Okay, what's the difference?
So model-based methods are all about building a model of the environment.
Okay.
So it's kind of like a blueprint of how things work.
Oh, okay.
And so they try to predict what will happen next based on the current state and action.
So it's learning the rules of the game, kind of.
Like learning the laws of physics in a video game.
Oh.
Understanding cause and effect.
So if it can predict what's going to happen,
Yes.
it can plan ahead better.
Precisely.
Okay.
But building accurate models can be very difficult, especially in complex real-world environments.
Yeah, that makes sense.
And that's where model-free methods come in.
Oh, so they don't need that model.
They don't require the model.
Okay, so what do they do?
They take a more pragmatic approach. They don't try to predict what will happen. They just learn from experience.
So like a black box.
Like a black box.
Yeah.
They figure out which actions lead to good outcomes without necessarily understanding why.
Like, I don't need to know the rules of the game. I just need to know what moves win.
Exactly.
Okay.
And so they're more adaptable to unpredictable environments where the rules aren't so clear.
Okay, so are there
Yeah.
different types of those model-free methods?
There are two key types that we'll talk about: Q-learning
Okay.
and policy gradient methods.
Good.
And Q-learning is all about learning that action value function that we talked about earlier.
Right.
It tries to figure out which actions are the most valuable in each state based on the rewards it receives.
Okay. And what about policy gradients?
Policy gradients.
Yeah. How do they approach it?
They skip that value estimation step
Yeah.
and go directly for optimizing what's called the policy.
Okay.
And that's the agent's strategy for picking actions.
Uh-huh.
So they just focus on making that policy better.
So it's like fine-tuning the decision-making.
Exactly. Fine-tuning the decision-making directly.
Without needing to know why something is good.
Without the nitty-gritty details of why certain actions are good.
Okay.
And that can be very effective, particularly when you have a ton of possible actions to choose from.
So we've got model-based versus model-free.
That's right.
We've got value-based versus policy-based.
That's right.
So it seems like there's no one right way to do it.
Yeah, that's right. There's no silver bullet.
It just depends on the problem you're trying to solve.
Absolutely depends on the problem, how complex the environment is, the type of rewards you're getting,
Right.
the computational resources, you have all sorts of things.
Okay, so this is all really interesting stuff. It seems like we've just scratched the surface of how these RL agents learn and
Yeah.
make decisions. But there's one big piece of the puzzle we haven't talked about yet,
Okay,
which is exploration versus exploitation.
that's right.
Can you explain what that is?
Yeah, so this is a classic challenge in RL, and it actually applies to humans as well.
Okay.
So imagine you're at a restaurant.
Okay.
You're trying to decide what to order.
Yeah.
Do you stick with your usual,
All right, my go-to.
your go-to safe bet? Or do you try something new
Yeah.
that could be amazing or terrible?
Yeah. So in the world of RL, that go-to would be exploitation.
Exploitation, that's right.
Using your knowledge to get the reward,
That's right.
but the trying something new, that would be exploration.
Exactly.
Okay.
And finding the right balance between these two is critical.
Right, because if you exploit too much,
Yeah.
you might miss out on something better.
Exactly.
But if you explore too much, you're just wasting time.
We're wasting time on things that don't work.
Right. So how do these algorithms
Right.
balance that?
So one common approach is what's called the epsilon greedy strategy.
Epsilon greedy.
It's a very simple idea. You basically choose a random action
Okay.
with the small probability, which we call epsilon,
Okay.
and then you exploit your current best knowledge the rest of the time.
So it's like flipping a coin every now and then.
That's right.
Just to keep things
Just
interesting.
to see if there's something better out there.
Yeah. And you can adjust how often you do that.
You can adjust how often you do that, and that's actually a common technique.
Oh, okay.
Early on, you might want to explore a lot,
Yeah. Just figure out the lay of the
to
land.
figure out how things work.
Okay.
But as the agent gets more experience,
right. Then
you
you
can reduce that exploration
exploit that knowledge.
and focus on what you know.
Okay. So one more distinction
Yes.
in the notes here.
Uh-huh.
On policy versus off policy learning.
That's right.
What is?
So this is about how the agent learns from its experiences.
Okay.
On-policy learning means the agent is learning from actions taken by the same policy that it's currently using.
Oh, so it's learning by doing?
Learning by doing, constantly refining its strategy based on its own actions.
Okay, what about off-policy?
Off-policy learning is a bit different. The agent can actually learn from data that was generated by a different policy.
Oh, interesting.
So it's like learning by watching someone else play the game
Oh, okay.
or studying historical data.
So you can learn from others' mistakes.
That's right. You can learn from others' mistakes.
Yeah.
And this can be very powerful, especially when it's expensive or
Wow.
time-consuming to interact with the environment.
Like in the real world.
Exactly.
Okay, but I imagine there are trade-offs between these two approaches.
There are trade-offs.
Yeah.
On-policy learning is usually faster and more direct, but it can be more sensitive to noise.
Okay.
Off-policy learning can be more stable and make better use of data,
Uh-huh.
but it might learn a bit more slowly.
So again, it's finding that balance
It's all about finding the right balance
for your problem.
for the problem you're trying to solve.
Okay.
That's right.
So we've gone over a lot here. The basic concepts.
We have.
Agents, environments, rewards.
Yep.
All the way up to these different methods.
That's right.
And it's amazing to see how much complexity goes into making these AI agents look intelligent.
It is a lot of complexity, and this is just the beginning.
Oh, right.
There's a whole world of RL algorithms out there,
Okay.
each with its own unique way of solving these challenges.
Well, I'm ready to dive into those.
Okay.
Maybe we should let all this sink in for a minute.
Yeah, good idea.
We'll be back soon to explore this exciting world
The world of RL algorithms.
of RL algorithms.
Stay tuned.
Stay tuned.
Welcome back.
Okay, I'm ready to see how all this comes together.
All right.
So our notes mention a few categories of these algorithms.
Okay.
Value-based, privacy-based,
Mm-hmm.
and something called actor-critic methods.
Right.
What's the difference?
So think of it like different approaches to learning a new skill,
Okay.
like playing the piano.
Okay.
Value-based methods are like meticulously studying music theory and practicing scales.
Okay.
They're all about learning how good each note or chord is,
All right.
and then using that knowledge to compose music.
So they're understanding the value of each element
Exactly.
before putting it all together.
That's right.
Okay, what about policy-based?
Policy-based methods are more like learning by ear.
Okay.
You might not understand all the theory behind it,
Uh-huh.
but you can figure out which combinations of notes sound good,
Okay.
and you learn to play a song that way.
So just going for it.
Yeah, just going for it, just trying to improve the overall performance without necessarily understanding all the individual pieces.
Okay, and what about these actor-critic methods?
So actor-critic methods are kind of like having a teacher guiding you as you learn.
Yeah.
So the actor is the part of the algorithm that's actually playing the piano, trying things out.
Okay.
The critic is like the teacher providing feedback on how well the actor is doing.
So it's a combination of learning by doing
Right.
and getting feedback.
And getting expert guidance.
Okay.
Exactly.
That makes sense.
All right, so let's dive a bit deeper into one of the fundamental algorithms in the value-based world,
Okay.
temporal difference learning, or TD learning.
TD learning. Okay.
Yeah.
I remember seeing that in the notes.
Yeah,
Can you break it down for us?
absolutely. So imagine you're trying to predict how long it will take you to get to work each morning.
Okay. Yeah.
You might start with a simple estimate based on the distance and typical traffic.
Right. But I'm guessing it doesn't always go according to plan.
Of course not. There are always unexpected delays, a traffic jam, a train crossing.
Yeah.
You hit all the red lights. Those differences between your prediction and the actual time it takes, those are the temporal differences.
So the gap between expectation and reality.
Exactly.
Right.
And in TD learning, the agent uses those temporal differences to update its predictions.
So it's like, okay, I was off by 10 minutes today.
That's right.
Let me adjust my estimate for tomorrow.
Exactly.
Oh.
And one of the simplest forms of TD learning is called TD0.
TD is 0.
And it's like a short-sighted learner. It only looks one step ahead.
Okay, so very immediate.
Very immediate, just focused on the immediate consequences.
Got it.
Now, remember Q learning that we talked about earlier?
Uh-huh.
It's actually an extension of TD0
Okay.
that specifically deals with those action value functions.
So it's all connected.
It's all connected.
Okay.
So it uses temporal differences to figure out which actions are the most valuable in each state.
So Q learning is like a specialization of TD learning.
That's a great way to put it, yeah.
Okay, but are there any downsides to this approach?
Yeah, so there can be, and your notes mention something about overestimation bias.
Yeah, what's that?
Yeah, so Key learning, especially when you use complex models like neural networks, can sometimes be a bit too optimistic in its estimates. It might overestimate the value of certain actions, and that can lead to not so great decisions.
So it's like being overly positive.
Yeah, like having rose-colored glasses on and not quite seeing reality clearly.
Okay, so how do you deal with that?
So there are techniques to mitigate this bias. One common approach is called double Q learning.
Double Q learning.
Which uses two separate networks to provide a more balanced and accurate estimation.
So like getting a second opinion.
Exactly like getting a second opinion.
Okay.
To double check those overly optimistic estimates.
Okay.
All right, so we've covered value-based methods like TD learning and Q learning.
Yep.
What about those policy-based methods?
Yeah, how are they different?
They take a more direct route. They don't bother with estimating values. They just focus on optimizing the policy.
Okay, so cutting to the chase.
Cutting to the chase.
Okay.
Figuring out the best actions without needing to understand all the details of why they're good.
And this can be more efficient.
It can be more efficient, especially when calculating those values is really difficult or computationally expensive.
Okay. Are there any specific algorithms in this category?
There are many, but one classic example is called reinforce.
Reinforce something.
And it works by collecting data from the agent's interactions with the environment.
Okay.
And then using that data to directly adjust the policy to make it more likely to choose actions that led to those high rewards.
So learning from experience.
Learning from experience, that's right.
Okay. But are there any challenges with this?
Yeah, so policy-based methods can be powerful, but they also have their quirks.
Okay.
One challenge is that those updates can be a bit noisy and unstable.
Okay.
Leading to slow or erratic learning.
So not always a smooth process.
Not always a smooth process. Think of it like trying to fine-tune a radio signal.
Okay.
You might overshoot or undershoot the perfect frequency as you're adjusting the dial.
Right.
So there are techniques to smooth out that learning process.
Okay.
One common approach is to use an advantage function.
An advantage function.
Which helps the algorithm focus on actions that are significantly better than average.
So the really good ones.
The really exceptional ones.
Okay.
Yeah, and by incorporating these refinements, we can make policy-based methods more stable and efficient.
Okay, so we've got value-based, policy-based, each with their own little variations and quirks.
That's right.
It can be kind of overwhelming. How do we know which one to use?
Yeah, that's the million-dollar question.
Yeah.
Choosing the right algorithm is often more of an art than a science.
Oh, wow. Okay.
It depends on the specific characteristics of the problem, the complexity of the environment, the nature of the rewards.
So many factors.
So many factors and the computational resources that you have available.
So it's like having a toolbox full of specialized tools.
Exactly.
And you have to know which one to grab.
You got to know which one to grab for the job.
Right.
And we haven't even talked about those actor-critic methods.
Right.
Which combine elements of both value-based and policy-based approaches.
Yeah.
But that's a topic for another time.
Okay.
Let's take a break to process all this algorithmic awesomeness.
Okay.
And we'll be back shortly to wrap up our deep dive into modern reinforcement learning.
Welcome back to our deep dive into reinforcement learning.
We're back.
I feel like we've covered so much.
We have covered a lot.
But there's still more to explore.
There is always more to explore. That's what's so exciting about this field.
Yeah, speaking of new stuff, our notes mention Trust Region Policy Optimization, or TRPO.
TRPO.
Yes.
What's that all about?
So TRPO is designed to address a really important challenge in policy-based methods.
Okay.
Making sure that when you update the policy,
right,
you don't accidentally make it worse.
Oh, so like the policy is how it makes decisions. Exactly. It's the agent's strategy for choosing actions.
Okay.
And we want to improve that strategy, but sometimes taking a big step in what seems like a good direction can actually backfire.
Okay.
And lead to a worse policy.
You don't want to go backwards.
You don't want to go backwards, exactly.
So how does TRPO prevent that?
TRPO tries to prevent that by taking more cautious steps.
Okay.
It makes sure that each update to the policy stays within a safe region, where we're confident that the policy will either get better or at least not get significantly worse.
So it's like putting guardrails on the learning process.
That's a great analogy, guardrails on the learning process,
okay,
to prevent those catastrophic drops in performance.
Makes sense, but how does it actually do that?
It uses a pretty clever mathematical trick to measure how much the policy is changing.
Okay.
And it makes sure that those changes stay within acceptable bounds.
Sounds complicated.
It can be computationally demanding, and that's why there's another algorithm called Proximal Policy Optimization, or PPO,
okay,
which tries to achieve similar stability, but with less computational overhead.
So it's like a more efficient
a more streamlined version of TRPO.
Okay.
And it's become very popular because it's effective and relatively easy to implement.
So it actually works.
It actually works, yeah.
Now, before the break, you mentioned actor-critic methods.
Yes.
Can you remind us how those work?
Of course. So remember the analogy of the piano student and the teacher?
Yeah. The actor is the student trying to play.
The actor is the student.
And the critic is giving feedback.
The critic is the teacher providing feedback.
Okay.
So the actor is focused on learning the policy, the best actions to take.
Right.
And the critic is focused on evaluating how well the actor is doing, providing more nuanced feedback than just the raw rewards from the environment.
So more than just good job or bad job.
Exactly. It's like saying, hey, not only was that a good note, but it was also much better than I expected given the current chord progression.
Okay, so more detailed feedback.
More detailed feedback, exactly.
Yeah. All right, are there any popular actor-critic algorithms out there?
There are several. A popular one is called Advantage Actor Critic, or A2C.
A2C, okay.
And it uses the idea of an advantage function that we talked about earlier.
Right.
Measuring how much better an action was than expected to guide the actor's learning.
So it's highlighting those really good moves.
It's like the critic is providing constructive criticism.
Okay.
Highlighting both the good and the bad aspects of the actor's performance.
So it can learn from its mistakes.
It can learn from its mistakes. That's right.
Okay, and this leads to faster learning.
Faster and more stable learning.
Got it. Is there another one?
There's another powerful one called Soft Actor Critic, or SAC.
SAC.
Okay, what's that one do?
It's designed to handle situations where the agent has a ton of possible actions to choose from.
Okay, like a really complex situation.
A really complex situation, yeah, and it encourages exploration by incorporating randomness into the decision-making.
So it's not afraid to try new things. Not afraid to try new things, even if they seem a bit risky.
Okay.
And this makes it particularly well-suited for tasks that require a lot of dexterity or fine motor control, like robotic manipulation.
Oh.
You know, like a robot trying to grasp an object.
Right.
It needs to be able to explore different ways of moving its arm and fingers.
Yeah, so how does all of this connect to deep learning?
That's a great question. The combination of reinforcement learning and deep learning has led to what we call deep reinforcement learning, or deep RL.
Deep RL. Okay, so it's using deep learning.
It's taking the power of deep learning.
In the context of RL.
In the context of reinforcement learning, exactly.
That's it. So deep learning, that's like those artificial neural networks.
Those artificial neural networks that can learn really complex patterns from data.
Right, and so you're applying that here.
Exactly. And deep neural networks are really good at handling high-dimensional data, like images or sensor readings.
Okay.
And this is crucial for a lot of real-world RL tasks, where the agent needs to process a lot of information to make decisions.
So like a self-driving car would need that.
A self-driving car, absolutely. It needs to process information from its cameras and sensors to make safe and efficient driving decisions.
So our notes mentioned deep Q networks, or DQNs. What are those?
So DQNs were a major breakthrough. They combined Q learning. Remember that algorithm for learning action value functions with deep neural networks. And this allowed RL agents to learn directly from raw sensory input, like pixels from a video game screen.
So instead of having to hand design features.
Exactly. You can just let the deep neural network figure it out.
It learns it on its own.
It learns it on its own.
Okay, that sounds powerful.
Yeah.
But I imagine there are still challenges.
There are definitely still challenges. One challenge is sample efficiency.
Sample efficiency? What's that?
Deep neural networks typically need a ton of data to train effectively.
Okay.
But in RL, collecting that data can be really time-consuming and expensive, especially when it involves real-world interactions.
So it's like having a hungry learner that needs a lot of food.
That's a great analogy, a very hungry learner.
But it's hard to get that food.
And getting the food can be a real bottleneck.
Right. Are there ways to deal with that?
There are. Researchers are working on ways to make deep RL more data efficient. One technique is called experience replay.
Experience replay.
Where the agent can actually learn from past experiences multiple times.
Okay.
So it's like reviewing your notes
to
make sure you really understand the material.
Okay. And is stability still a challenge?
Stability is still a challenge. Training these systems can be a bit like trying to tame a wild beast.
Yeah.
Things can go wrong in unexpected ways, and the performance can fluctuate a lot during training.
So it's not always a smooth ride.
Not always a smooth ride.
But it's getting better.
It's getting better. Researchers are developing new techniques to improve stability all the time.
Okay, so what's next for RL? What are some of the big questions for the future?
Well, reinforcement learning is still a relatively young field. There's so much more to discover. One exciting area is model-based RL, finding more efficient and accurate ways to learn models of the environment.
Right, so it can plan ahead.
So it can plan ahead and make more informed decisions.
Okay.
Another important area is safe RL.
Safe RL. Okay.
Making sure that these agents operate safely and reliably in the real world.
Especially when mistakes could be dangerous.
Especially when the stakes are high.
Yeah, like with a self-driving car.
Exactly. You don't want the car making a wrong turn into oncoming traffic.
Right.
And of course, there's always the ongoing quest to improve sample efficiency and stability.
Right. Make it more practical.
Make it more practical, exactly.
Well, this has been an incredible journey.
It has been a fascinating deep dive.
I feel like we've learned so much.
Me too. And remember, the world of RL is constantly evolving, so stay curious, keep exploring, and who knows, maybe you'll be the one to make the next groundbreaking discovery.
That's right. And to all our listeners, thank you for joining us on this exploration of modern reinforcement learning. We hope you've enjoyed it. And until next time, keep those brains buzzing.